That was neat. Is it? I don't know what I'm looking for. I just saw it from afar. It's okay if not, but it was neat because you could do the spotlight. I see. Yeah, I was very lucky to have you go last week, and so I could scope out yeah. Sorry. Cool. Okay, cool. Thank you. Yes, testing. Is this okay? Cool. Thank you. I don't know if we still have a minute or two, or do you want to start?
Hello everyone. So we're very happy today to listen to Eion Blanchard, who's going to speak about decidability bonds for Presburger arithmetics extended by sine.
Cool. Thank you. And of course, thank you to the organizers for inviting me to speak. As Esther mentioned, I'll be speaking on decidability bounds for Presburger arithmetic extended by sine. Oh, and this is all joint work with my advisor, Phil Peronomy, who will be arriving tomorrow. So first, I'll give just an overview, introduction. So as we all probably know, Presburger arithmetic is the first order theory of the integers with order and addition. And in 1929, its namesake mathematician, Presburger, showed consistency, completeness, and decidability for the theory. And that's sort of the branching off point for this. In this seminar this morning, Philip mentioned this research program that looks in part at extensions of Presburger arithmetic, and so that's more my sphere here. And so a lot of work has been done in this area, and so a few examples of previous results on extensions of Presburger arithmetic include the first one here, where we have the theory of the natural numbers with order and addition, as well as the exponential function, of course, just on the natural numbers, so we don't quite have full multiplication. And in fact, the full theory is decidable. On the other hand, if we extend our universe to the real numbers and maintain a predicate for the natural numbers, now, as I mentioned, this exponentiation function defines full multiplication, and so we get undecidability through piano arithmetic, which is undecidable. Okay. Another example, if we have the real numbers, order, addition, multiplication, and the base E exponential function, this theory is again decidable, and that's a conditional result under Chanel's conjecture, which I'll talk about in the second half of the talk. If Chanel's conjecture holds for R, and this is the result of McIntyre and Wilkie. Okay. And then if we swap out this exponential function for the sine function, instead of decidability, now we have undecidability, and that's because we can pretty easily define the integers using the sine function. And again, we sort of can invoke piano arithmetic to give undecidability. Okay, and then sort of a last example, if here now from the last one, if we switch out multiplication in favor of a predicate for the natural numbers, we still have undecidability. This is a lot less trivial than the previous one, and it's a result of Peronomy and Konovich. And so the point in all of these examples is that there's like no clear pattern, and if we take an extension by this function or consider the reals or the natural numbers as our underlying set, there's no immediately clear pattern in terms of decidability. And even within that For the undecidability results, we might wonder what fragments of this theory are decidable. And that's really what this talk is about, specifically for the fragment of this last theory where quantification is restricted to the natural numbers. And so we still have the reals as our underlying set because the sine function, of course, takes natural numbers outside of the natural numbers. And so we have to be a little bit more formal about that. But in spirit, we want to think of this as the extension of Presburger arithmetic by the sine function. Okay, and that's what I'll be talking about today. So again, as I mentioned, sine Presburger arithmetic, or sine PA for short, is the fragment of that final theory where we have the reals, order, addition, predicate for the natural numbers, and the sine function, with quantification restricted just to the natural numbers. That's what we'll mean when we say sine PA. And so we can establish the signature for that, L sine. And then we define sine PA sentences as, exactly what I've been saying, just these L sine sentences, specifically in pre-next normal form. That's mostly for convenience. And again, with quantification taken just over n. So this will be true for the first half of the talk. And in the second half of the talk, I will secretly change this definition to mean quantification taken over z. That just sort of makes it easier for the second half of the talk. But that change is, it doesn't have any impact on the results, and you can, change between them without real consequence. And again, for, if you're thinking in terms of model theory, we're considering the truth of sine PA sentences over like the standard model. So like nothing crazy is meant to be happening under the hood. And so just an example of a sine PA sentence we have here. We could stare at it and maybe guess its truth value. I can spoil it. It is true. And it's witnessed by x1 equaling 0, which, with the sine function just makes everything easy because that 0, propagates through. And so this is just to get a feel of, what these expressions of sine PA sentences look like. And so the main results that I've gotten with my advisor, Phil Peronimi, so far are these two bounds on, what we could call like a decidability threshold for this fragment, where in terms of quantifier complexity, we, switch over the fragment from, some decidable fragment into undecidability. And so as sort of like an upper bound to this boundary or an undecidability result, we have that sine PA sentences with just 4 alternating quantifier blocks are undecidable. And in fact, we have an explicit bound on that. The 3,388 itself doesn't so much matter, but we do have an explicit finite bound on that. And then on the other side, we have the decidability result, which we can think of as a lower bound to this, decidability, undecidability threshold. And that is that the existential sine PA theory is decidable, though this is conditional on Channel's conjecture. In fact, Channel's conjecture for the complex numbers, which again, I'll talk about, what that entails in the back half. So let's get started on that upper bound result. So basically the way that we get, yeah, go ahead.
So you mean for k greater or equal to this?
For the first result, is that you're asking? Yeah. Like if we just take the sine PA sentences where like we have, at most 3,388 existential quantifiers, and then at most the same number of for all quantifiers, and then, bounding the number of quantifiers, even taking just that set is undecidable. So think of it as at most. Does that clarify? Cool. So yeah, the way we go about this, essentially we're going to capture the theory, the monadic second order theory of the grid, which is undecidable, capture that in sine PA, and that will essentially give us the result. And so the method for this follows that of Hieronymi, Nguyen, and Pak in their work on alpha Presburger, which was the extension of Presburger arithmetic by multiplication by a fixed irrational number alpha. And in that they had this Ostrowski enumeration system that they worked with the sine function instead of this limited multiplication. We have to do something different in terms of the technology, but in spirit it's sort of doing the same thing. And so the first step of that is to approximate natural numbers using the sine function. That will be sort of the basis of the encoding that we're ultimately building. And so first we start out with the definition. If we have two natural numbers, d and x, we say that the best approximate of x up to d, and we'll denote it by x bar d, that's going to be the natural number that's at most d, which best approximates x from the left under sine. So, we can think of this as like an argmax for the sine. We have it written out here. It's the y such that the sine of y is like the y or the z, I guess, that gives you the maximum sine value without exceeding the sine value of x. I also might refer to d as a degree of approximation. Cool, and this is probably best visualized. So here we have a picture. It might be a little small for those attending in person, but if we consider the best approximation of 550 up to 10, the way we can think about that is by having this sort of, mesh on the interval -1 to 1, and we, can sort of mark all of the sine values of natural numbers up to our degree of approximation, in this case 10. And so you can see at the top, oh, I can use this. Let's see. There you go. Yeah, at the top, we have all the numbers 0, 1, 2, 3, 4, all the way up to 10. And so then we're trying to approximate 550. And so we think of where its sine value lands. And basically, we're just looking to the left of that and seeing what number gives us that bar. So in this case, we're looking for 550. And so we go to the left and we find sine of 6. So we would say the best approximate of 550 up to 10 is 6. And in fact, this shaded region, every natural number whose sine value falls in that shaded region is best approximated by 6 up to 10. Okay, and then we can do that with as fine a mesh as we want. We could take the approximation up to 50 instead of just 10, and we find that in that case, approximating 550 gives us 50 itself. And I chose that because it was like the next best approximate. Like if we only took the grid or the mesh up to 49, the best approximate would still be 6. So that's not like immediately clear, but I know that, and that's why I chose these examples. Cool. So once we can approximate, individual natural numbers, then we can sort of beef that up and approximate differences under the sine function. So here we have two pairs of natural numbers, x bar and y bar, and we have this function g, which essentially is capturing the difference of differences. You'll notice like a slight asymmetry because the x2 and x1, they don't have their own absolute value, and we don't need to worry about that in this context. That's just to sort of force the order among sine x1 and sine x2. Specifically, we want sine x2 to be larger than sine x1, but for the y's, we don't care. Okay, and so with that, we can define a relation called best that holds precisely for tuples DE, x bar, which again, think of as x1, x2, and y1, for which there's a y2 such that the y pair is a best difference approximate up to d and e of x. Okay, and that's in quotes because I don't have time to define that super clearly, but hopefully the words convey the meaning here. D and e are just the degrees of approximation for the valid pairs y1 and y2 that we're sort of considering. And that's specifically for the second condition with this g function, which again, think of it as just like the difference of differences. So we want that to be as small as possible without capturing the exact pair. And that's what I mean when I say for all z with z and y set distinct. That just means they're like different and not just like order swaps because of this symmetry. Okay, again, this might be better visualized. So now we have a very fine mesh. We have up to 100 and up to 140. So the dark orange all around, oh no, sorry. The dark orange marks the mesh up to 100, and then there's like a faint pink mesh as well that adds on up to 140. And so here, if we're considering, whether or not this predicate best holds or not on this tuple, we're basically asking, okay, if we're trying to approximate the difference between sine of 50 and sine of 550, this predicate is asking, is 70 and like sine of 70 a part of a best difference approximate for the difference between sine of 50 and sine of 550? And the answer is yes. And in fact, that other entry to the pair y is 109. And we can sort of see this. This is what we're trying to approximate, the difference between these sine values. And we find that the closest approximate on this mesh is the blue shaded region, 70 and 109. Important things here are that given the first 4 entries to the tuple, there are at most 2 satisfying 5th entries, in this case 70. But if we pick the degrees of approximation, these first 2 entries, if we pick the first one low enough, we can make it so that there is just going to be 1 sort of satisfying value, in this case 70, because 109 can't, since 109 is greater than 100, we couldn't flip this and say best of this with 70 replaced by 109. That would not be witnessed by 70 because 109 exceeds the coarser mesh. And so that's important because like this 70 number here is like essentially what we use this predicate to encode natural numbers with. And so that's why the fact that there's just like 1 that can exist if we pick the parameters wisely enough, that's why that sort of works. Okay. So as I mentioned, we build this up yet again, and finally, we're going to encode arbitrary finite subsets of N2, which is what we need to do to capture the monadic second order theory of the grid, like I mentioned at the beginning. So to this end, we define another relation called member, and it holds for tuples where we have 4 natural numbers. We can think of them as parameters, and then 2 other natural numbers s and t, such that there exist all of these degrees of approximation. We don't need to worry too much about them, but specifically such that we have the best predicate holding on the respective d1, e1, d2, e2, where sort of that last entry of the first one with s holds and the last entry of the one with t holds. Sort of again, think back to this picture and how I pointed out the like sort of uniqueness of the 70 in this case for best to hold. And so in that light, we can kind of think of these conditions encoding s and t, which we'll see on the next slide, as well as some other more like technical constraints that we don't need to really worry about it. It's mostly just like bookkeeping with the best approximates to ensure that we can like decode the encoded set in a sense. Okay, and in terms of getting an explicit bound on these undecidable sentences in the end, it is important that member can be written as an EA sine PA formula. That will help give us the explicit bound. And so then we have the theorem that promises the encoding. And that's namely, if we have a finite subset of n squared, then there exists some 4 parameters of natural numbers such that for all pairs of natural numbers, the predicate holds with s and t as like the last 2 entries, if and only if s and t form a pair of whatever our set was. Okay, so member here is, as we saw in the previous slide, it's a fixed relation. what depends on S are these parameters x1 through x4. Okay, and so the way we determine these parameters from our set S briefly is we just sort of enumerate them, and we build these 4 sequences sort of all at the same time, building them up with like successively best approximates. And we have 2 of these sequences managing these increasing degrees of approximation, which were like all those D's and E's that we saw on the previous slide. We have a 3rd sequence which distinguishes the parity of indices, aka like which, if we think of the enumerated values comprising the pairs in the set, basically like where do the pairs actually sit? That way we don't actually accidentally like decode a pair like C2 and C3 when it's supposed to be like C1 and C2 and then C3 and C4. And then the last sequence actually encodes the numbers S and T in the ways I've been stating it, using the best relation that we saw before. And then if we build this correctly, we don't need to consider the full sequences because it's all sort of built in for us, and we can just consider the final entries of those sequences, and that'll sort of encode everything that came before. Okay, and so here's a theorem from the alpha Presburger work that I mentioned of Hieronymy, Nguyen, and Pak, where they obtain essentially the bound that comes from considering the monadic 2nd order theory of the grid with some predicate that has exactly the property that we just noted that our member relation has. So in particular, if we have a first order, yeah. Oh, yeah, sorry.
When someone asks a question that enters an audience, the virtual audience, someone who repeats it.
Thank you. Okay, is this okay? Cool. Right, so as I was saying, if we have a 1st order expansion of the natural numbers with order and addition by some predicate with exactly this property that I mentioned our predicate had, aka there are parameters where we can encode with if and only if any finite subset of the grid, then we have that deciding EA sentences with that predicate and some bound, the particular bound doesn't matter, appearances of that predicate, we get undecidable sentences. And so sort of combining that with the fact that our member relation has the desired property and itself was EA definable, we get that EA sentences in sine pi are undecidable. And again, the particular number just sort of follows from counting appearances, basically. Yeah, and that's the first result. Yeah, so Alexi asks, sort of where does that K come from? It's not from counting appearances of sine, it's from counting quantifiers. And so I mentioned when we introduced member, it's EA definable. I didn't say how many of these, I forget the exact number, it's not many. But it's sort of just like counting everything like written out and then putting it in pre-next normal form. which is just like tedious is the main thing. And yeah, so yeah, counting quantifiers is the key there. Cool. Any other questions on sort of this is the first half? Now.
Does the predicate, do you have to have the predicate n, or is n somehow findable from sine? What happens if you remove the predicate n?
That's a good question, and I'll address that towards the end of the second half. So for people online, the question was, what if we didn't have a predicate for the natural numbers in this setting? And the answer to that will come by the end of the talk, because it's very relevant for the decision procedure that I'm about to present. So I'll wait until then. Any other questions? Doing okay. Okay, cool. So again, that was sort of the upper bound, the undecidability result. So now on the other hand, we have a decidability result, albeit one that's conditional. And again, we can think of this as sort of like a lower bound to this threshold between decidability and undecidability. Okay, so here's the diagram. Again, if we remember from the introduction, the result is going to be that the existential theory of sine PA is decidable. And so I'm going to present a decision procedure. And I did mention that it depends on assuming Chanel's conjecture holds for C. And so in this diagram, these blue like double bordered steps are those which currently use Chanel's conjecture. So just taking us through the diagram, we start with an existential sine PA sentence. And then first, we're going to use Chanel's conjecture to manipulate the literals in our sentence and get a sentence which has no appearance of sine in any of the equalities. And then for some further simplifications, we don't need Chanel's conjecture, and we can get rid of the equalities with variable replacement, and then eliminate linear appearances of variables from the inequalities, which I'll speak more on that when we get to that step. And then once we have these sort of simplified inequalities as the only literals that appear in our sentence, then we can pass to what I call a proxy solution set in the real numbers. And then that is in a setting where we don't need the predicate for the natural numbers. And we can pass to a theory which is decidable also under Chanel's conjecture. And we can essentially query, is there a proxy solution in this other decidable theory? If there is, then that means there is an integer solution to the sentence that we started out with. Okay, so now let's talk about this first step of eliminating sign from equalities. Again, this is the first use of Chanel's conjecture, which I think I introduced on the next slide. And so just for notation, for this half, I'll write x to mean like an n tuple of x variables, which generally will have vary over the integers. And then we have the dot product as denoted. And yes, as I said this at the beginning, but in the first half of the talk, we were quantifying over the natural numbers. Here we're doing it over the integers. So just so you know, this is where that switch is happening. Again, it's inconsequential, it's just convenient, essentially. And so we start with sort of a fact that helps us organize the syntax so that we can more clearly apply Chanel's conjecture. And that's by noticing that if we have any L-sign term, then we can write it in this special form, this dagger equation, where we have these rational vectors, whatever, where we can write the L-sign term, as a sum of just linear appearances of the x variables in a constant plus a sum of signs, where the arguments to the signs are just like Q linear combinations of our variables and other L-sign terms, which themselves we can organize as each being sign applied to something else. And specifically where that something else is like a lower T term. This will maybe be clearer in the next slide with an example. Basically, this is just like an unnesting scheme where we're adding a lot of T names just to be able to clearly organize things and have specifically this form of the TIs of X be just sine applied to some argument rather than, the more general setting of L-sign terms where we can have, sines and linear appearances together, as we see in the Dagger equation. Okay, before that example though, another definition is we'll call an L-sign term oscillatory if when we write it as in this Dagger equation form, basically this part is 0. So we can think of this as an oscillatory L-sign term is just like an actual sum of signs with no like linear terms on the outermost layer. But of course we can have like linear appearances within some sign argument. That's still okay. Otherwise it would have to be variable free. Okay, so as an example of what this, applying this Dagger equation or this nesting scheme looks like, we have this example L-sign term t of x. I've already like ordered things in the way of the Dagger equation where we have here, I guess we can say n is 2. We just have x1 and x2, but we have, sort of the linear appearances of the variables first, and then after that it's a sum of signs. But in order to really do this, we want to define these other L-sign terms t1 and t2 so that we can write t as just the linear terms and constants plus sine of a q-linear combination of linear variables, constants, and t terms, where we sort of define these t terms separately, where they're each sine applied to something lower. So in this case, we started out with something that had sort of like 3 nested applications of sine. And so we have to unpack those by having, t2 standing for sine of t1, where t1 itself is already that innermost sine. And so in the outermost level, we just have sine of t2 within that first argument. And then since the second sine, wasn't nested, we don't need to change anything for it. Okay, so that's all this is. It's just like an organizational thing. It's not anything tricky. Okay, and so then some definitions. Because as I mentioned, sort of this first phase of the decision procedure is to simplify the literals that we're considering in the matrix formula of the sentence that we're trying to decide. It's helpful, I think, to name these types of literals just so we can speak about them somewhat more intuitively, if you believe that I've named them all. So the ones that we'll need in this case, basically we have 2 types each of inequalities, equalities, and disequalities. For the equalities and disequalities, we consider L-sign equalities and disequalities as, as what they sound like, where it's an equality or a disequality of L-sign terms, where we allow, thinking again in the form of that Dagger equation we worked with, thinking of, one side being 0 and the other side being written in Dagger form with a linear part and then an oscillatory sine term, aka just like a sum of sinusoids. And then for each of those, we also have the L equality and L disequality, where we don't have any sine terms and it's, just in, Presburger itself without sine, if you will. And then we also have the inequalities, which their distinction is a little different. So we have the normal L-sign, there we go, L-sign inequalities. Here we have the oscillatory sine term on the right-hand side. And then what we deem an oscillatory L-sign inequality is where we have no linear appearances of x, aka we have a constant on the left and then a strictly oscillatory L-sign term on the right-hand side. So again, a sum of signs, there's no like x1, x2 appearing unless it's within the scope of some sign application. Okay, so now we can actually do something with this. And so for that, I'll introduce Shanel's conjecture if you aren't familiar. So this is open, and the way I've stated it is just for C, but you can see it. Like we might say Shanel's conjecture for any particular field. I think for one of the results in the introduction, I mentioned that that result only required Shanel's conjecture holding for the real numbers instead of all the complex numbers. For this talk, it'll always be the complex numbers, which is why I won't say it anywhere else. And so the statement is that if we have n many complex numbers, then we have a lower bound on the transcendence degree of the field extension over Q of those complex numbers and their exponentials. And we can bound that transcendence degree below by the Q linear dimension of those complex numbers. Okay, so again, this is a conjecture, it's open. People who are more expert than me say it's out of reach, like being able to prove this, but I think people generally believe it to be true. And there is also, as we saw in the introduction, a precedent of results that are considered useful while being contingent on this conjecture holding. Okay, and so in our case, again, with the goal of eliminating sine from equalities, the first real thing that Chanel's conjecture gives us is that if we have a particular L-sine equality, so again, an equality of L-sine terms, and if we write it in the dagger form that we've been speaking about, if we have a particular solution to that equality, this z, and here we quantify over q, sort of just because we can, you could do it over z and it would still be true. But if we have that, this z is a solution to the equality, and if we have k greater than 0, which if you don't remember, k is just how many signs you need in the outermost. Okay, and so in this example, we had k was 2 because we needed to write it with 2 signs in the outermost expression. Okay, but this lemma has that if k is positive, so if there's like a sign appearing there, we have this thing which looks kind of complicated, but just means that there's some argument in that outermost sign, in those outermost signs, where either one of the arguments is 0, or there are 2 arguments to different signs that have the same absolute value. Okay, and so basically what this lemma allows us to do is simplify things down, right? Because if we remember that sine is an odd function, this second property gives us that, okay, if one sine argument is negative or equal of the other, we can combine those into a single term. And then of course, the first property is maybe more clear. If there's some sine argument which is 0, obviously the sign of that argument itself is 0. So again, we can sort of simplify down. And that's really the utility of this lemma that first uses Chanel's conjecture. Okay, and what that sort of builds into for us is this first reduction step where we have a particular L-sine equality, and we can effectively compute a Boolean combination of strictly linear equalities, or L equalities, which is equivalent over the rational, so has the same set of rational solutions as our originating L-sine equality. Okay, and that's about all I'm going to say about that. Over that. Okay, so that was sort of the first step, and then the second and third step of the first phase of this decision procedure is, I mentioned, eliminating equalities, which again I said is just variable replacement in sort of the obvious way, and then more interestingly, removing linear appearances of variables from the inequalities now that we've gotten rid of all the equalities of our literals. And so what we end up with is a Boolean combination of oscillatory L-sine inequalities, which was my name for inequalities that don't have these linear appearances. And we have that this Boolean combination is not equivalent like we saw with the earlier result, but it is equisatisfiable over the integers with our original conjunction. And again, another difference with this result is here we're going off of a conjunction. So, the previous result and this result don't immediately feed into each other. You have to, you can put it in conjunctive normal form and distribute the existential quantifier, but we don't need to worry so much about that. The point is here we can simplify the types of literals that we need to consider down to just oscillatory L-sine inequalities so that we don't need to deal with linear appearances of variables, which will enable what happens next. I'll remark sort of the trick to get rid of these linear appearances is sort of inspired by linear programming. and searching for the feasible set. And if you want to think about the feasible set for like a linear program, if there is an element of the feasible set, there's going to be one near the boundary in a sense. And so in the setting of Presburger extended by sine, we can think of that as sort of like linear programming with like wavy boundaries in a very rough sense. And so then the key is that the linear expressions that we're sort of comparing to these oscillatory boundaries, those are going to only be able to take like a finite number of values in the range of values that the oscillatory term can take on. And so that allows us to finitely enumerate those values and then further replace those and simplify. So I'll note that both of these steps actually are very inefficient. I think like at least like doubly exponential in terms of length of the sentence. So not efficient, but it works. Cool. So once we sort of have the ability to consider just conjunctions of oscillatory L-sign inequalities, we have this handy lemma, which affirms that now if we consider solutions over the real numbers instead of the integers, we have that the solution set has two important properties. One, it's going to be the union of equivalence classes modulo 2 pi applied coordinate-wise, and also is either going to be empty or have non-empty interior. Okay, and so what these do for us is say if we're looking for an integer solution to this conjunction, the fact that the solution set is a union of equivalence classes mod 2 pi, that means we can just look within the interval 0 to 2 pi for a solution. And then the non-empty interior says, okay, not only can we just look at class representatives in 0 to 2 pi whose class contains some like integer tuple, because the real solution set has non-empty interior, we can just look at any what we call proxy solution, i.e. it doesn't need to be equivalent to some integer tuple mod 2 pi. And that's sort of where we get this term that I mentioned at the beginning when we looked at the diagram, this proxy solution set. So here, if we have an L-sign formula, phi, for its use, we can think of phi as a conjunction of oscillatory L-sign inequalities, as I mentioned. We say that the proxy solution set, again, over the real numbers is a set of y, which are tuples in 0 to 2 pi such that the real additive group with sine, which again, we can think of as our original setting, but no longer with a predicate for z or n. If that structure models the existence of some solution, which is equivalent mod 2 pi coordinate-wise to this y. Okay, and this is essentially formalizing what we sort of thought through in this slide. Okay. And so then that gives us, specifically in the case where phi is a conjunction of oscillatory L-sign inequalities, we have that, this formula has an integer solution if and only if this real additive group with sine models the existence of a proxy solution. Okay, and so we've at this point reduced the decision procedure from existential sine PA to the theory of the real additive group with sine. In fact, the sentence on the right is also existential. We can define, for this M phi, we can define equivalence mod 2 pi and also membership in 0 to 2 pi without quantifiers. And so the good news is that this theory is decidable, that we've now reduced to. This is sort of the second use of Shannon's conjecture. And this is like a very reduced form of a result from McIntyre and Wilkie, where they gave the conditional decidability. Of this theory, the real field with restricted sign. And we don't need all of that. We only need for this result, like we don't need multiplication in there. So we're using something that's much stronger than what we need. And so maybe there's a way to not use Chanel's conjecture here, but we already used it earlier, so it doesn't so much matter in that sense. But again, the point is, if we have decidability of this theory, we can then sort of derive decidability for the theory with unrestricted sign, which is, again, what we need here, because that's the theory that we reduced existential sign PA to, in a sense. And so that gives us the second main result, which is if we assume that Chanel's conjecture holds for C, then we have that the set of existential sign PA sentences is decidable. And that's the talk. So here are some references. Thank you. I'm happy to take questions on either half or anything else as well.
Thank you very much. Are there any questions?